So this part is on linear models. Linear models are for looking at correlations between two continuous variables. So we're looking at numbers. The example that I have up here is looking to see a relationship between an individual's average glucose levels and their BMI. I'm showing you 11 values. If we were to say, is there any relationship between average glucose levels and BMI? We might take a look and say, like, in totality, the lowest value is 70 on the average glucose side, and the lowest value for BMI is 102. So 148 looks kind of low. The highest average glucose level is 228, highest level is 240. It looks like as you get higher glucose levels, you get higher BMI. But we're really bad with looking at numbers. We can't put any stats to this. It's just a visual trend. So if we can move this into a formula or get some like data visualization on it, that would be better. So we're going to take our data, put it into a linear model, or sometimes we call it fitting a linear model to our data. Imagine a scatter plot with these two variables and you have the bunch of dots. You're fitting a line through it to try and get as close to all the points as you can. So that's why you're going to see fit. We're fitting a linear model on our data and then visualizing it. So for simple linear models, we're looking for a relationship between two things, a predictor and a response. This is also kind of tricky because we're so many names. We're trying to predict whether we can use glucose levels to predict the outcome of BMI, predicting the response of BMI. We're inputting glucose levels for the output of what do we think their BMI is. So you'll see these names kind of used interchangeably for input, independent, and predictor. The reason why the second one is the dependent one is because we're trying to see if BMI depends on the glucose level. So you see how these are arrows? This is a directional relationship. We're trying to see whether one influences the other. It's not a two-way street. You can make the other comparison, but this is evaluating like a one-way thing. This is more important, especially when you're moving on to the mixed models or like complex multiple ones, because it is a directional comparison. So with these, we think that there's a relationship between these two variables. We need to collect some data or some observations to support it. Like that data table we saw on the previous slide, now we have these different observations. Is there a relationship between these two variables? Also have to keep in mind that we have a large element of noise and error. Sometimes we can take this into account. A lot of times we kind of live in a silo on R and hope that it is as perfect as we can get. But keep in mind that there is always going to be error that we need to account for. We're not going to be able to, or at least in working with a lot of human data, we never expect a perfect model to come out because we know there's so many other covariates that are going to be affecting the response. So to visualize what we're doing, we have our X and our Y variable. We're trying to fit a regression line through it, fit our linear model on top. We are trying to draw that line so that it's as close to all the dots as possible. And we'll get back to mathematically how that works out. So back here, we have our dependent and our independent, the input and the output. We think, or we're hoping that there's a relationship between them. How do we draw a line? The two things that we're going to change is going to be first our slope. So the slope is multiplying the independent variable. So if we have a positive slope, this would be our first example in which if we're looking for a correlation between weight and height, generally somebody who is heavier is going to be taller. That's a positive correlation, right? On the other hand, a negative slope would be if you have a higher viral load, you have a lower chance of survival. So that's like a negative correlation. And if you have a straight line, unfortunately, that means you have no correlation, and that's not a very good predictor. Because at that point, you're just getting random noise and dots all over the place. If you are keeping in mind for mixed models, this MX would be MX plus MX plus MX. So each of the variables you're trying to model would have their own slope. So the one with the largest number has the most influence over your response, right? So this might be, if we're looking at height and weight, we would see maybe, or height and weight, maybe smoking has like a lesser effect, a lower slope compared to diet. And the other thing that we're looking at for these models is going to be the y-intercept. So where do we draw the line in that plot? We only have one y-intercept no matter how many additional variables you have. So if you add more variables, you'll have mx plus, and then always the b at the end. And what doesn't really get captured in what we're doing today is keeping in mind that there is that kind of stormy cloud of the error that should be brought through as well. So when we're making a linear model, R gives you a lot of information back. It really takes, I think, less than 5 lines of code to run a linear model. The hardest part, I think, when we're learning this is how do we interpret the responses that are coming back? So the object that I have called the output is called fit because we fit the linear model. And I'm looking at a summary of this. This is a complex object that has a lot of slots and is trying to make a very nice report for you. So let's walk through it. The first thing that it's telling you is the call. It's a little bit like notes to let you know this is a comparison at the start of the report. So when you're doing summary fit, you might be making a bunch of different models. This is more just record keeping to tell you what was a comparison. Remember that tilde that we looked at earlier? We see it here again. So the formula of LM, the linear model that we're fitting, is average glucose as a function of BMI. So there is that directionality. We're seeing how much influence does glucose have on an individual's BMI. And then the data that we're getting is from the heart data set. Next up is residuals. Residuals is the difference between the observed and the expected value. So if we look, for example, over here, we can say maybe this is an X of 10. In a perfect world, if we had a perfect correlation, we would expect all the Y values to be touching the line. But there is a difference between what is expected that intersects our regression line and the actual observed points. So this point is a little bit higher. The difference between the observed and the expected, that distance is our residual. And when we're fitting a linear model, we're trying to minimize the residuals on all points. So if we had that really low one down there, it would have a really high residual. And we can't just add up all the residuals because we have some pluses and some minuses. And the at least most common in my field that we see is for fitting this regression line is a least squares, least being minimum, squares because we square the residual so that everyone is a positive, and it also increases or adds a little bit of the scale so that the outliers have a larger influence. So that regression line, we're trying to really minimize that effect of the really far data points. So this is all kind of discussions of what's going on under the hood. The most common method of this would be least squares to minimize the size of the residuals, get the line as close to as many of the observed spots as possible. We rarely really need to, I think in my day-to-day, take too much look at the residuals, but this is important to report back because this is how the regression model is built. The coefficients was what I was talking about in the previous slide, mx plus b. So we have mx plus b, glucose as a function of BMI. So we can say here, what is the coefficient that is modifying BMI? That would be this, 0.11. So this is a scale factor for BMI. It's at the linear model is estimating the slope to be 0.11. And the y-intercept, listed as intercept over here, is estimated to be 88.6. So this is how we can build our y equals mx plus b. from here. The other thing we want to take a look at, so for every increase in BMI, there is an increase in average glucose level, is like the human readable side of this. We also have our multiple R squared. So this is a percentage of variance in Y explained by X. We know that there's a lot of messiness going on with human data, so we only have 3% explained. But we know that there's a lot of factors going into BMI. Genetics is a big part of it, smoking, diet, all that other jazz as well. And before I move on to that, which I forgot to highlight over here, these 3 stars at the end, this is telling us significance. So BMI has a coefficient of 0.11. Is BMI having a significant impact on the average glucose level? Statistically speaking, we have 3 little stars, meaning that it's a very, very low significant score, which is good for us. So to highlight the 3 important things that we want to look at, the direction of the effect, this is a positive value. So as BMI increases, average glucose is also increasing. The size of the effect, 3% of the variance in average glucose can be explained by BMI. And while this is maybe a small number, this is statistically significant based on these test scores that are returned to us. So this is my overview of what we would be looking for when we are doing our linear models. It will always give you back the same output in this structure. You can pluck out the different slots if you want to move forward to something else, but this is the beginnings of how we would look at the linear models. And then I think we have an example of visualization when we get into it. Any questions? Anything we want to review in the slide deck? Yes, that's p-value. So these are like the p-values, and your alpha value would be like your cutoff. So generally speaking, 0.05, right? So we want to see if this is less than 0.05. If you're doing a lot of testing, there might be like multiple testing correction that you need to do. But yeah, generally we're looking at that less than. We have over here, 1 dot is 0, like if it is 0.05, it's a dot. If it's like, I think 0.01, then it's this. No, I think that's backwards. Star is 0.05, 2 stars is 0.01, and then 3 stars is 0.001. It gives you that range. Here, you can kind of, whoops, and see a little bit better. So anything between 0 and 0 and 0.001 is 3 stars. Anything between this is 2 stars. Anything between this is 1 star. And then anything kind of like bigger is like close, but not there. And then not really caring. Yeah, so we have these stars at each of them. So this is saying that the intercept is significant and that this coefficient is significant. So technically, when you're running this, if you want to add more variables, you just add it into this equation over here and you get a very similar output with more lines coming down here to say this slope is this, next slope is this, next slope is this, and there's more significant values. So it actually is computationally very similar. Shall we give it a try? What do you mean?
Like, it seems very low. Like normally I'm looking for something like 0.9 plus range for my regression values, my R-squared values.
Yeah.
Like I'm working with like really simplified systems. Is this how it works with human biology?
This doesn't surprise me too much because I'm thinking like if I'm looking at something that's predicting average glucose levels, that your diet is going to be a lot more than your BMI. There's other things that are going to be affecting it more strongly. So this isn't too surprising for me. Yeah. And the problem is that we don't, at least in my data sets, we don't have a lot of the covariates to be correcting for. So we just have to like swallow it as noise, right? Yeah.